In this question we're given a complex number, z equals to minus 3 plus I, and we're asked to raise it to the power of 4, and we're told that we should use de Moivre's theorem in order to do this. So to use de Moivre's theorem, you have to convert your complex number into what's called polar form, and that's not the form we're given it in the question. In the question we're actually given it in Cartesian form or rectangular form. So let's have a look at the complex number on the Argand diagram, and our complex number is minus root 3 plus, and I'm going to write 1 times I just for clarification. 1 times I is the same as I. Minus root 3 is approximately equal to minus 1.7 plus 1I. And on an Argand diagram we plot that the real part, which is this part here, is equivalent to the x-axis, and the imaginary part is equivalent to the y-axis. So our point is approximately minus 1.7 on the real axis and 1 on the imaginary axis. And if we join those two, we get the point shown here. So that's where Z1 is. And in order to apply de Moivre's theorem, we have to write our complex number in a slightly different format, in what's called polar format. So in polar format you specify your complex number in terms of a magnitude and an angle theta. And the magnitude is the distance from the point back to the origin, the length of that light blue line on our diagram. And the angle is the angle that that line back to the origin makes with the positive axis, and we typically call that angle theta. How do we work out the magnitude? Well, it effectively comes from the distance formula in coordinate geometry, but it's a simplified version of it because one of our 2 points is 0, 0. That means the magnitude always simplifies out to be the square root of the real part squared plus the imaginary coefficient squared. And in our case, the real part squared is minus root 3 squared. The imaginary coefficient is 1, and we've got to square that as well, which is just 1, and then we get the square root of all of that. Minus root 3 squared is 3, and 1 squared is 1, so that gives us the magnitude of Z1 is equal to the square root of 4, which is equal to 2. This really should have the magnitude symbol as well. So we now have our magnitude. What about the angle? Well, there's a formula for the angle, and the angle is theta is equal to the inverse tan of the imaginary part over the real part. The imaginary coefficient over the real number. But we have to be careful about two things here. First of all, that angle has to be it doesn't have to be, but the convention is that we use radians as the unit of measure for angles in complex numbers, not degrees. And the second thing we have to be wary of is to make sure we get an angle in the right quadrant. So in our case, if we were to fill in the values there, we get the inverse tan of the imaginary over the real, so that's 1 over minus the square root of 3. And if we put that into our calculator, let's just stick with degrees for a moment because most students are more familiar with degrees. The angle we would get is minus 30 degrees, which is an angle on our diagram round about here. And that's going to give us the wrong complex number. It's going to give us a complex number here. So what we have to be careful of is when we're working out the angles for complex numbers, when we're converting to polar form, is to make sure we're in the right quadrant. The safest way to do this is to work out the equivalent angle in the first quadrant and then use that to figure out the angle in the quadrant of interest. So if the angle was in the first quadrant, we would work it out as the inverse tan of 1 over plus root 3. So to be in the first quadrant, the tan value has to be positive, so the 1 needs to be positive, the root 3 needs to be positive, and that would give us an angle of 30 degrees. So that's our equivalent angle in the first quadrant. So we know that we've got an equivalent angle of 30 degrees in the first quadrant. What does that translate into in the second quadrant? Well, what you do is you take your angle from the first quadrant and make an angle with the x-axis in the quadrant of interest. So in other words, I would make a 30-degree angle here, and that gives me my line or radius of interest, radial line of interest. So if I have 30 degrees there, I can work out what this angle here is. It must be 180 less 30. So my angle of interest is 180 degrees minus 30, which is equal to 150 degrees. And if you check in your calculator, you will find that the tan of minus 30 degrees, which is the incorrect angle that the calculator would give us, is equal to the tan of 150 degrees. So the calculator is correct in telling us that the angle is minus 30 degrees to get a tan of 1 over minus root 3. The problem is it's one of two correct answers, but only one of them is correct from the question point of view, from the complex number point of view. So just to recap, best way to do these is to work out the equivalent angle in the first quadrant by making everything positive. Sketch the location of your point in the Argand diagram, thereby determine which quadrant it's in, and then use that angle from the first quadrant to figure out the corresponding angle in the quadrant of interest, in this case 150 degrees. So having said all that, I'm going to wipe some of that out because we should really be working in radians. So we just showed it in degrees there because sometimes that's easier to work with for students. But in actual fact, the values we should be working with are radians. So instead of minus 30 degrees, that would be minus pi over 6. And that means we have an angle here of pi over 6. We make an equivalent angle in the second quadrant, also pi over 6. And then this remaining angle here must be 180 degrees or pi less pi over 6, which is equal to 5 pi over 6. So we now know that our angle in radians is 5 pi over 6. So we can write our complex number now in full polar format as follows. So for full polar format, we write the magnitude, which we've already worked out is 2, times cosine of 5 pi over 6 plus I sine 5 pi over 6. And if we multiply that out, if we work that out in a calculator with our calculator set to radians mode, and actually work out what the cosine of 5 pi over 6 is and multiply it by 2, we'll get minus root 3. And if we take 2 and multiply it by the sine of 5 pi over 6, we'll get 1. So that will give us our plus I. So this polar format is just an alternative way of writing the same thing. The advantage of having it in polar format is we can now apply De Moivre's theorem. So De Moivre's theorem will tell us if we want to raise that complex number to the power of 4, we raise the magnitude to the power of 4, and we multiply the argument or angle by 4. So in this case it's cosine of 4 times 5 pi over 6, which is 20 pi over 6, and I sine 20 pi over 6. 2 to the 4 is equal to 16, and the cosine of 20 pi over 6 is minus a half, or minus 0.5. And the sine of 20 pi over 6 is minus root 3 over 2. And if we multiply that by 16, we get minus 8. And if we multiply minus root 3 over 2 by 16, we get minus 8 root 3 times I. And the question specified that we should give our answer in the form of a plus b root c times I. And that's what we have here. Our a is equal to minus 8, our b is also equal to minus 8, our c is equal to 3, and we have our I. And that's the answer